The lifetime of an electronic device is distributed as an exponential random variable with mean mu equal 20 years and standard deviation sigma is 20 years. A random sample of 50 of these devices is selected. Tam, a graduate electronics engineer, is interested in the sample mean lifetime of the 50 in the sample. State the distribution of the sample mean lifetime justifying your answer. So x bar is going to be a normal with a mean of 20 and a variance of 20 squared divided by 50. We know that there were 50 devices. Now, as far as justification is concerned, you know that n is more than 30, and therefore you can state that the distribution for sample means should be normal. And of course, you know where the 20 squared over 50 comes from. Remember, this is standard deviation, and it's always variance here in the normal. So we have to square that, but divide by 50. Determine the probability that the sample mean lifetime is between 15 and 25. So that's probability of x bar being between 15 and 25. And we can get that straight from the calculator. So interactive, and we'll be doing normal CDF with the lower of 15, an upper of 25. Now our sigma is going to be 20 over the square root of 50. Yeah, remember this one is the variance. And the mu is 20. And that will give us 0.9229. Jai, the chief engineer, informs Tam that the lifetimes may not be exponentially distributed, but could be a more complicated distribution, yet still having mu 20 and standard deviation 20. If Jai is correct, will your answer to part B change? Explain. Well, first of all, no. And the reason is that since we have n greater than 30, the sample means should follow a normal distribution as stated, irrespective of the underlying distribution. A different random sample of size n of these devices was selected. Repeated sampling with this sample size shows there's a 3% chance of obtaining a sample mean greater than 25 years. Determine the value of n. So what we're being told is that here's 25, and this is 3%. Now, if we want the z-score value for that, we can find that from the calculator. So what we want is an inverse normal, and we'll tail set to the right, and the probability is not 0.3 but 0.03, and that gives us 1.8808. Now we're talking about a different distribution of size n, but our mean is the same, and the standard deviation for a standard one was the same, so it's just going to be 20 squared over n this time because we've got n in our sample. So we're being told that the probability of this resulting in a value of 25 or more is 3%, which gave us this z value. So if we think about this from the point of view of a confidence interval, what we're being told is that going from the middle at 20, so if we're going upwards, that's going to be the 1.8808 times 20 over root n. We're being told that that is equal to 25. And so 1.8808 times 20 over root n is equal to 5. So we can solve that on the calculator. So action, advanced, solve. So we've got 1.8808 times 20 over the square root of x is equal to 5. And that gives us that x is 56.59. So n is 56.59. Of course, this is one of these situations where you always round up. So we'd say that n was 57.